this is about equilibrium. And here we've got a very good example of what equilibrium is all about. So here is the Haber process. The Haber process is represented by the equation below. As you can see, nitrogen gas reacting with hydrogen gas to give us ammonia. And then they say the delta H is 0. Now, there's a few things to understand here. One, do you see this double arrow here? The double arrows simply indicates that this is a reversible reaction. That's what the double arrow means. It is a reversible reaction. That means there is two reactions that are occurring here. There is the forward reaction and there is a backward reaction. The forward reaction is the one in which nitrogen is combining with your hydrogen to give you ammonia gas. This is the forward reaction. And then there is a backward reaction. The backward reaction or the reverse reaction is the one in which ammonia is now breaking down to give you your hydrogen and your nitrogen. Right, so these are the two reactions that are occurring, but we write them like this, and we use this arrow that shows it's a reversible reaction. It can go forward, it can also go backwards. What does the delta H means? There's a delta H less than 0. That's telling you that the forward reaction, meaning this one here, the forward reaction is an exothermic reaction. That is why the delta H is negative. That means it is producing heat. So heat is a product. That's what it means. Heat is a product. The forward reaction releases heat to its environment. And that means this reverse reaction must be using up heat. So you can see I'm just writing the same equation, this one like that, and then I write this one in reverse. Now what that means is a forward reaction is exothermic and the backward reaction is endothermic. So if I have a reversible reaction and the forward is exothermic, then the backward is endothermic. Or if the forward is endothermic, then the backward is exothermic. Right, that is very important to understand because remember when we talk about the factors that affect equilibrium, one of those factors is temperature. And remember we said when we talk of temperature, we're going to think of heat. Now there is a question that we can answer here. They're saying the percentage yield of ammonia increases with an increase in pressure at a given temperature. Give a reason for this. But remember those three things we said affect equilibrium. Number one, we said it's our temperature. We said concentration. We also mentioned pressure. So remember with pressure, that was the last thing I explained. So I'm just going to give you the answer here quickly. We're saying if they increase pressure, we find that there is more ammonia. How do you explain that? We go back to Richard-Lear's principle and say Richard-Lear's principle states that if a disturbance is introduced to a system, the system will react in such a way that it counters that disturbance that has been introduced. So what does an increase in pressure means? If you increase pressure, that means you are decreasing the volume. If we look at our equation, 1 mole of nitrogen combines with 3 moles of hydrogen. That means the total number of moles on this side of the equation is actually 4, which relates to 4 volumes. That means this side will occupy 4 volumes at STP, so it will be 4 times 22.4. And this side has got only 2 moles. That means 2 volumes on this side of your equation. Now, this side has less volume, this side has more volume. So if you increase pressure, how will this system relieve that pressure? So if you increase pressure, you're going to force this system to have a smaller volume. So you're going to favor the forward reaction. More nitrogen and hydrogen will combine to give ammonia, which occupies a less volume, a smaller volume. And this will relieve that pressure that you have increased. So what they have done here, when they say, what they've asked, when they say, give a reason for this, the percentage yield of ammonia will increase with an increase in pressure at a given temperature. So you explain it according to Lee-Chatter's principle, increasing pressure on the system would want to relieve that pressure by favoring a reaction that produces less volume. In other words, the forward reaction will result in a lower, in a smaller volume. That will be your reasoning on number 7.1. That's how pressure would affect this one. So if you increase pressure, you favor the forward. You decrease pressure, you favor the reverse reaction. Someone might ask, how will temperature affect this one here? Remember, we are not talking of rates of reaction here. We are talking of percentage yield. In other words, how much of this is there and how much of this is there. So if you increase temperature, this reaction, as you can see, the forward reaction is exothermic. The backward is endothermic. If I increase heat, or if I increase temperature, that means I've added more heat to the system, and the system does not like that increase in heat. So the system will favor the reaction that removes that heat. And in this case, the reaction that is removing heat is the reverse reaction. So if you increase temperature here, you favor the reverse reaction, because the reverse reaction uses up that heat. So you have an increase in nitrogen and an increase in hydrogen, and then a decrease in ammonia. If we lower the temperature, we're going to have an increase. We're going to favor now the forward reaction, because the forward reaction will replace that heat that you have taken out. That means you have a decrease in nitrogen, decrease in hydrogen, and an increase in ammonia. Right. So when we do the Haber process, you will see that there will be a compromise between using a higher pressure. Remember, using a higher temperature. Remember, if you use a higher temperature, you also increase the rate of reaction. But the problem with this one is that if you use a very high temperature, yes, the rate of reaction will be high, but you're going to decrease the yield. So you have to get to a temperature where it's favorable to have a good rate of reaction and also a good yield. Right, going to questions. Of course, these ones, they would like to give questions. But before we go to questions, let me just remove this quickly. Right. A mixture of nitrogen with an initial concentration of 0.5 moles per dm cubed and hydrogen with an initial concentration of 1.5 moles per dm cubed are placed in a closed 1 liter container. When equilibrium is attained at a certain temperature, 25% of the original nitrogen is consumed or used up. Right. First of all, we need to be able to write the Kc value, which we spoke about yesterday. Kc value. How do you write a Kc value? Let's take a hypothetical equation. Let's say 2 moles of A gas reacts with 3 moles of B in aqueous to give us 4 moles of C, which are also a gas, plus 5 moles of D, which is a solid. Let's just say it's a hypothetical equation that I'm using. Not real, but for the sake of explaining, we're going to use this one. If I'm asked to write the Kc value for this one or to calculate it, I'm going to say the equilibrium constant is going to be the concentration of the products. In this case, the product is C, concentration of C to the power of the number that is in front. So the equation needs to be balanced to the power of 4 multiplied by, now here is an interesting thing. If I put D here, so we don't include anything which is a solid on our Kc. Because remember, it's a 1. Even if you include it, it's like 1 to the power of anything. Or anything that is solid or anything that is a pure liquid, we don't use it in our Kc. So the D we are not using. But if the D was aqueous or gas, we could have used it. Over the concentration of A, the reactants now, to the power of 2 multiplied by concentration of B to the power of 3. And these concentrations need to be used, you must use the concentration at equilibrium. Yeah? So I would like you guys, for this question, just to write the Kc for this particular reaction that we are doing for the Haber process. So I'm just going to let you write it down. Then I will ask and I will show you how I would have written it. Ne? So let's have a minute. Let's do it. Then I'll come back to you. Right. Tatu. Sorry, Tando. I think yours is Tando.
Sir?
Yes, have you completed it?
No, sir.
All right. How many more minutes? Still working on it.
Yes, sir.
All right, I'll come back to you. I saw Tato Monare. Where have you gone? Tato?
Sir?
Yeah. Have you completed it?
No, sir.
No. Okay. Are you? Is it challenging, or you were not here yesterday?
Yeah, I was struggling to log in yesterday, sir.
Okay. All right. So you sort of have no idea what's happening here.
I have no idea what's going on, sir.
Okay. Just keep watching. You'll catch up. Then you
Okay,
can check the other video. We have posted it, I think, on YouTube.
okay, sir, I'll do so.
All right. Katleo.
Sir,
Yes, you were here yesterday. What do you have?
no, I was not here, sir.
You were here. I was with you. I remember you were here.
Ish, ish, ish.
Okay, it's not a problem. Let's do it together. Kc here for, right, let me just clear this. So the Kc value is going to be, look at our products. These are our products. and those are our only products here, and they are gas. So we include them. We say concentration of ammonia to the power of 2, because there's a 2. First of all, the equation must be balanced over the concentration of the reactants, in this case nitrogen, and nitrogen, there's no number in front of it, meaning it's 1, so to the power of 1 is the same as just saying concentration of nitrogen gas, and it's a gas, that's why we're including it, multiplied by the concentration of hydrogen to the power of 3, because there's a 3 in front. This is how we're going to calculate the equilibrium constant. And equilibrium constant, it's a number, it's more of a ratio that will show us the ratio between the reactants and the products. So we'll know if we have more of the products or we have more of the reactants. Now, this is how your Kc value will be calculated. But the challenge will be we need the concentrations at equilibrium. We need the concentrations at equilibrium. Without the concentrations at equilibrium, we cannot calculate it. This now brings us to the next part, where we need to draw what we call a rice table. Rice table, we'll use it when we do acids and bases more and all that, but the table is simple. Let me just do it quickly here. Then you guys can also practice with right. The space doesn't look nice here. Let me create space. So we had said our Kc is equals to concentration of NH3 to the power of 2 over concentration of nitrogen multiplied by concentration of hydrogen to the power of 3. So when we do our rice table, we need the equation. So nitrogen is combining with hydrogen in the ratio 1:2 to give us ammonia, 2 moles of ammonia. So in your table, this is how you draw your table. Let's divide like that. So on your table, the first column, I'm going to write Ni. This means the initial number of moles that are there. So on the top, we write the equation N2 plus 3H2 to give us 2NH3. Right, 1 mole of nitrogen will combine with 3 moles of hydrogen to give us 2 moles of nitrogen. Then I write Ni on the first row. Do you see the first row? Ni means the initial number of moles that are there before the reaction starts. Then the second row is going to be, you can write the N reacted. N reacted. It means the number of moles that were reacted. The number of moles that were reacted. Then the third one, we can write the number of moles at equilibrium. And the fourth one, we're going to calculate the concentration at equilibrium. This would help us summarize everything so that it makes sense. If we just throw things around, it is not going to make sense. So they are saying a mixture of nitrogen with an initial concentration of 0.5 moles. So there is 0.5 moles of nitrogen and hydrogen with an initial amount of with an initial concentration. Sorry, I think I've made a mistake there. Let's redo it. They're saying a mixture of nitrogen with an initial concentration of 0.5 moles per liter and hydrogen with an initial concentration of 1.5 moles are placed in a closed 1 liter container. When the equilibrium is attained, 25% of the original nitrogen is consumed. So they gave us concentrations, that the initial concentration. So we need to convert the initial concentration to actual number of moles. Remember, we say concentration is number of moles over volume. So for nitrogen, they are saying there's 0.5 moles per dm cubed is equals to number of moles over the volume, which is 1. Now, when you multiply 0.5 times 1, you are going to get that there's 0.5 moles of nitrogen. So I had sort of ran without explaining that. Remember, the liter is the container is 1 liter or 1 dm cubed. So that means we've got 0.5 moles of nitrogen initially. We also have 1.5 moles of hydrogen being placed in the container. But what we don't have is the ammonia. So there is only 0 of ammonia. There's nothing, there's no ammonia. And this is our situation. And I'm going to slow down. I think the video is, the screen is very slow compared to what I'm saying. So I'll wait for it. Okay. So we've got 0.5 moles of nitrogen initially, 1.5 moles, 1.5 moles of hydrogen, 2 moles of ammonia. Then how much was reacted? We don't know. How much is at equilibrium? We don't know. We need to come up with that one. So they say when they reach equilibrium, at a certain temperature, 25% of the original nitrogen has been consumed. So 25% of nitrogen has been consumed when they reach equilibrium. So we can do our calculations there and say what is 25% of 0.5? That's what we need to calculate. So 0.25 times 0.5. That means 0.125 of nitrogen is used up. That's what they are saying. So 0.125 of nitrogen is used up. So this is used up. For reactants, we say used up. So we need to subtract that value from the original we have. But before we do that, we can work out all the other values of the other items. For example, here, if nitrogen, we use 0.125, how much of hydrogen was used up? Nitrogen S to hydrogen, the mole ratio is 1:3. So if 0.125 of nitrogen was used, how much of hydrogen was used? You can do your simple calculation and would say 0.125 times 3. That means 0.375 moles of hydrogen was used. These values, we're supposed to subtract them from the original because they are being used up. So how much of ammonia is produced? Mole ratio is 1:3. between ammonia, nitrogen, and ammonia, it's 1:2. So double the amount of nitrogen used up is the amount of ammonia that is produced. So 0.125 times 2, you get 0.25. So plus 0.25 moles of ammonia is produced. So how much do we have at equilibrium? For ammonia, it's simple and straightforward. It's going to be 0.25. For hydrogen, it's 1.5 minus 0.37. 1.5 minus 0.375, which is going to be 1.125. And for nitrogen, it's going to be 0.5 minus 0.125, which will give you a 0.375. Now remember, you need the concentrations at equilibrium so that you can substitute those values into your Kc. And concentration is calculated as number of moles over volume. In this case, remember your volume, it's a 1 liter container. So everything, number of moles over 1, number of moles over 1. That gives us a concentration here of 0.375 moles per dm cubed for nitrogen and 1.125 moles per dm cubed for hydrogen and 0.25 moles per dm cubed for ammonia. You bring your values to your Kc to calculate the Kc. Concentration of ammonia 0.25 squared. And notice that I'm no longer using square brackets because now I'm working with numbers, over concentration of nitrogen 0.375 to the power of 1. So we're putting nothing there. Multiplied by, for hydrogen, we said 1.125 to the power of 3. And this would give you your Kc value, and you get your 8 marks. Do you see that there's a lot of work to be done there? There's a lot of work to be done, but if you put it in a table like this, it's easier for the teachers when they mark, or for the examiners when they mark. And it's also easy for you not to get confused. These calculations that I've been doing down here, you need to show them, and then you show your information on your table. All right. Let me just speak to you. What do you say? Anyone wants to say something? I know it's confusing, but I hope because it's a video, you can pause it, play it again, pause it, play it again. So eventually you'll be able to understand. Mr. Katleo.
Sir.
Yeah.
Yeah, I'm still calculating.
Oh, you're still calculating. Right.
Yeah.
Just hold on. Do you see that I've not put in a number here? The actual calculation, I know that one you can do with your calculators. This part I know. What I want everyone to understand is how to write the Kc value, what to look for, what to ignore, and what to take into consideration. Then what was happening here is the most important thing. So
Yes,
if you can remember, this video will be posted on our YouTube channel. You can go there. You can, I don't know, I was about to say rewind. You can, I don't, what do you call it? You play it back, and then yeah, you play it back, then pause it, play it back, and then you just follow through this one and try to do it on your own. This particular question, you've got it on your the CD that I gave to you. I saw your message, Kathy. I'll make a plan for you. I'll speak to
Okay.
Mrs. Bottas and see if we can have that WhatsApp group, and then I'll send it to you.
Okay.
Yeah? All right. I don't think I have much time. I've got 2 minutes now. Anyone with a question or anything you just want me to clarify? Others, you just quiet, eh? Lefa, nothing to say. Lefa, you are quiet. Or Diril?
Yes, sir.
Yeah. And
Yeah. I'm gonna have to
you rewind,
replay it.
like I said, Ed Cathy was laughing at me. Okay.
Yes.
Uh-huh. Then,
Because it's
yeah, but that's
so
the
new.
advantage, ne? If you can play back, then pause it, then just pause it for the sake of time.
Yes, sir.
All right, there will be follow-up videos on some questions like this one. That one I'm not going to be, that's not going to be on Zoom, it's going to be on your YouTube.
Okay, sir. Thank
All
you.
right, all right, okay, sharp. Mohadi,
Mr. Chimbunde.
yeah.
Yeah, yeah. We'll, like Udi said, we'll go back and watch the videos again.
All right, I'm definitely going to ask Mem to fix us a WhatsApp group then. But I'll be the only one that will be controlling it. I'll be the only admin and all that. Then we can post